We're going to turn now to some of the implications for quantum mechanics in a first year chemistry course, and in particular the specific energies that electrons have inside an atom. Again, quantum mechanics is in part a response to three issues in terms of the behavior of electrons. One is that electrons seem to be quantized inside an atom. They can only have specific energy levels. And the higher the energy, the further away from the nucleus. And also the higher the energy, the closer those differences in energies get together. So it's like a ladder, but a ladder without evenly spaced rungs. Also, electrons don't tend to follow repeatable and predictable trajectories. They instead exist in probability regions that we call electron orbitals, a place where you're likely to find an electron. And it gets even weirder than that, of course, because sometimes an electron is not even a thing to be found or a particle to be found. It's an energy wave that spreads out over that space because electrons exhibit what we call wave-particle duality. Sometimes they behave like energy, sometimes they behave like matter. And this is a pretty strange set of things to pull together. And so it produces for us a pretty strange conceptual framework for a model of the atom with the quantum mechanical model. What you see before you here is called an Aufbau diagram. It is the arrangement of possible energies that electrons can have. Each of those lines on that diagram represents a possible energy for an electron. And how you find that electron is related to a set of criteria. The first thing we look at is what's called the principal energy level. The principal energy level is just tells you, again, numbers 1, 2, 3, 4, first energy level, second energy level, third energy level, where higher the energy means further away from the nucleus. The second thing we'll look at is what's called an energy sublevel. And the sublevels are labeled with letters S, P, D, and F. And they represent the particular shape of an atomic orbital, which is again just a region of space where you're likely to find the electron. The number of sublevels is equal to the principal energy level. So in the first energy level, there is only one sublevel. In the second energy level, there are two. In the third, there are three, and so on and so forth. Within each sublevel are a set of orbitals. The orbitals, again, are the electron locations, the region of space where you're likely to find the electrons. And each sublevel holds a different number of orbitals. So an S sublevel has one orbital, a P has three, a D has five. And so when we look at how all this builds together for a model of the atom, each of these different types of sublevels describes a different shape. So at the first energy level, there's only one sublevel. And that sublevel is an S sublevel. An S sublevel has a spherical shape. So this would be a model for our 1s in 2 dimensions. It looks like a circle on the screen, but you have to keep in your mind these are 3-dimensional shapes, and it actually is a sphere. And so for the first element, hydrogen has only one electron. That electron can be found in the 1s orbital. Helium has 2 electrons, and its second electron is also in the 1s orbital. And this gets us to our last little piece of information here, and that is the concept of spin. Electrons spin on an axis. So when we are thinking of electrons as particles, they can spin around just like the Earth spins on its axis. And the thing about that is because electrons are charged, a fundamental feature of the universe is that moving charge generates a magnetic field. One of the primary forces in the universe is called the electromagnetic force. Electricity and magnetism are always linked. Moving magnets can create an electric current. That's how a generator works. And moving electric charges can generate a magnetic field. And so, 2 electrons which have a like charge should repel one another, but they can in fact exhibit the same orbital if they have opposite spins. So if one is spinning left and one is spinning right, one has an up magnetic field, one has a down magnetic field. And in this energy diagram, we typically record electrons, or we model electrons with arrows. Now again, electrons are moving around in 3-dimensional space. There is no up, there is no down. There's no horizon for an atom inside a compound. Spin is just a way to designate that there are two possible magnetic orientations, and those opposite magnetic fields can cancel out by attracting, can cancel out the propensity for two electrons to repel because they have like charge. So spin tells us that every orbital can hold two electrons, provided they are opposite spin. As we move across the periodic table, the next element on the periodic table would have 3 electrons, but you can't fit a third electron into the 1s, so we need ourselves a new orbital. We move to the second energy level. The first sublevel in the second energy level is the 2s. The 2s has the same shape as the 1s, but it's a little bit bigger because higher energy means further away from the nucleus. So for that next element, it has 2 electrons that are going to be found floating somewhere into that 2s location. Now, that 2s is a sphere. They're just as likely to be found in the blue region as well, but some distance away from the other electrons that are in there. Again, these are probability fields. One of those electrons has a probability of being on the next screen, but this is where they are likely to be found 90% of the time. So those 2 electrons would fill the 2s, and then we move into the 2p. There are 3 orbitals in the 2p, and the first one is labeled 2py. A p sublevel looks like 2 lobes, or flower petals, or propellers, whichever way you want to look at it. Both of those lobes represent the 2py orbital. An electron in a 2py is just as likely to be found on top as it is on bottom in this picture. And again, these are 3-dimensional. So you might think about like a blown up balloon in terms of the shape that would take in 3-dimensional space. Again, that orbital is going to hold an electron. We're going to label that electron as an upspin in the 2p. And then on the next electron is not yet going to pair up. It's going to go into the next 2p orbital, which is called the 2px. So you might be thinking what the x and the y mean. And when you look at there on the screen, maybe you already picked out that those represent axes, x-axis and the y-axis. And so we'll have an electron pop into that 2px. And so that's the next element on the periodic table. Then we would have the 2pz, which is going to be in the z-axis. So we're trying to represent it in a 2-dimensional space here, but you have to think about one of the lobes coming out of the screen, one of the lobes going into the screen. You can also notice that all of those p orbitals are tapered near the middle because that's where you're more likely to find the s electrons. And so there's a lower probability closer to the nucleus that those 2p electrons are going to be found. So we'll drop that other electron in the 2pz, and we'll put it into our Aufbau diagram or our electron energy diagram. And then we can go back, if we continue to move across the periodic table and add electrons, we'll pop electrons into those other orbitals, and then we'll also designate them as downspins, filling up the 2p. Now notice I've put some of them on the same side, some of them on opposite sides. Again, they have opposite spins, so they can occupy the same space. Essentially what they're doing is they're buzzing back and forth around the nucleus because they can't get right near the nucleus because the s electrons are all there. And then we move into the third energy level. The third energy level is going to have an s sublevel. It's going to look just like the 1s and the 2s, but of course it's going to be bigger because more electrons mean further away from the nucleus. Electron might drop in there somewhere. We'd get ourselves an arrow. We can drop in a second electron in the 2s, and then we'd get the down arrow. And where's our next electron going to go? Well, it's going to go in the 3p. It's equally likely to go in the y, x, or z. Again, there's no real orientation here. X, y, and z just tells us that there's 3 possible regions here. And so we would drop that electron in the 3py, for instance. It could just as likely go into the px or the pz. We'll fill up the 3p's and then the 4s. And then we would get into d orbitals, which are going to be a little too cumbersome to put into this diagram. This all seems really, really weird, but at the end of the day, and we're going to go through a set of steps on how to do this, all you're going to have to be able to do is put arrows in boxes. And the next video is going to show the series of rules you need to do that. Before that, though, just to give you an idea on what these orbitals look like, again, here's some three-dimensional renderings. An s orbital, again, is just a sphere, and it's like Russian nesting dolls. 1s, 2s, 3s, 4s are just going to be these spheres encapsulating one another. Here's a kind of a three-dimensional rendering of what the p orbitals look like. Again, here they're different colors, but that's one orbital. Both the top and the bottom represent a single orbital. Here's all the p orbitals kind of together. They look a little more like spheres stuck together. You'll see different renderings of these. The big issue is that they taper really not too much towards the center of the axes, and the electrons are more likely to be found on either ends. And then when you put them all together, it kind of shows you a rendering of that. And the d orbitals even get a little crazier. So the d orbitals have 4 lobes to each orbital, but again, notice where they are. The YZ orbital is everywhere the p orbitals are not. So rather than on the axes, they're in between the axes. And the letter notations there, YZ, XY, XZ, instead of now labeling axes, we're labeling planes on which those orbitals exist. And then, of course, there's that dz squared with the donut. And I have no explanation for you there why that donut is a thing. Here is kind of an image of what that looks like with those planes overlapped. And so all of those exist in a particular plane. And then we have the donut one. But then notice the hole in the donut, right, is where the s orbitals would be. So you can make some sense out of that situation. And then we go to the f's, and oh my goodness, what is going on here? These are crazy and all over the place. But you have to think about what's going on here, right? As we've talked about before. Why do we build these models? Well, we're trying to build a model for what it would have to look like for a bunch of electrons to get as close as they can to the nucleus and as far away as they can from each other. And the more electrons you get, the more complicated those spaces are going to be. The harder it's going to be to find a region of space that's not already occupied by some other electron. And so in these f orbitals, these electrons need a lot of options for where to be. And so all 6 of any one of those bubbles in these diagrams represent a possible location for an electron in an f orbital, and it's going to be in whatever one of those bubbles is not already occupied by some other electron until that electron moves to a different spot, and then it might move to a different bubble. And then go ahead and look at that FZ3, right? It's a double donut situation, but think about where those donuts are. They're above and below the d orbital donut. Again, bunch of electrons trying to get as far away as they can from each other and as close as they can to the nucleus. All of these are just mathematical models for where we might expect to find electrons, and this is what that mathematical model looks like. It's a mess. These are called wave functions. They're Greek letter psi. This is Planck's constant. Interestingly enough, there's imaginary numbers, square root of -1, right? There's imaginary numbers involved in this equation, and one would have to think, as crazy as this all looks, it would take quite a bit of imagination. All right, so in the next video, we'll look at how we go about putting the arrows in boxes.